in this video, we want to show that the shortest curve joining 2 points is a straight line. So we want to use the concept of Euler-Lagrange equation to get the shortest curve joining 2 points. Now, and we want to show that the 2 points being joined by the shortest curve is a straight line. So how do we solve this? Let's use black marker. Let us use black marker. So we have solution. It will be relevant to to suggest the points coordinates for the 2 points. So let's point A, comma y of A, and B, which is at B, comma y of B, be the two points, as in the figure below. We want to draw a figure that will represent the 2 points. So suppose we have something like this. Let's call this point B, and let's call this point A. Here we have B, the x coordinate is B, while the y coordinate is y of B. The x coordinate is A, while the y coordinate is y of A. Okay? Now, at this point, suppose this point, let's say that we have this. Suppose let's assume the curve is let's say at this point we have this, So let's call this one change in x, dx, and change in y. Okay, you can actually replace it by delta y or dy, and I write this one as the x when the limit is taken. So let's call this ds, which is the what? Which is the longest point, the longest line or curve joining this point and this point. Okay, now having done that, we are going to show that the x, is a length of a arc. How do we do that? Okay, now the length, let's write the length. I hope you can see that the length, the s of an element of the part be defined or be given as, let's say it's given as ds is equal to, let me clean this so that I'll be able to see what we're writing well. Given as ds is equals to dx squared plus dy squared raised to half. What do I mean by this? How do we get this? Fine. We got this from the concept of, if you use Pythagoras theorem here, this is what I'm trying to say here. I'm trying to say that I've cleaned the figure, but then let's say from here now, I want to get the s. This point to this point, we want to get it. Okay, we're going to apply what? Pythagoras theorem that says the square of the hypotenuse, so we can say, which implies ds, let's say dx squared, is equals to dx squared plus change in y squared. That is, change in x squared is equals to change in x squared plus change in y squared. Okay, so which implies you can find the square root of both sides. Change in x will be the square root of change in x squared plus change in y squared. So this can be written, let me clean it. This can be written as, oh, this is blue, sorry. Let me stop it. I don't want this blue. Okay, this can be written as, you can write this as factoring out, you can say dx squared into 1 plus the square root of this, dy, change in y over change in x all squared. Yes, if I factor out this, I'll have that. Yes, so which can be I'm just trying to show us how we're going to get the length of an arc here. The arc length, okay? As regards the point ds. So, which means I can have 1 plus, the square root of this is what? Is dx. I'll put it out there. 1 plus what? Dy dx, all squared. Then the square root of this and ds will be it. This will not cover it again. That is, I've found the square root of ds squared to be what? To be ds. Okay? Now the square root of this one is this. This square root will not cover dx again because it will only stop here. So the square root is just like square root of ds squared multiplied by square root of this. The square root of this, the square root of ds is dx. Now, if we take the limit as ds tends to 0, now, or this, I mean, taking limits as delta s tends to 0, now we divide through by what? Now, ds all over ds is equal to 1, the square root of 1 plus y prime squared, 1 plus y prime squared, which is the same thing as what? You can write it as what? Dx over dx is equal to 1 plus 1 y prime squared raised by half. So this is what? Is a length ds of what? Of an element of the part. That's the length. Yes. If I like, I might put my ds here. Okay. Yes. That's it. Okay. So that is the length ds of an element of the part, which we have defined here. So now, having done that, the next thing now we're going to do is to find the total part length. We need to find what? Total part length. Therefore, the total part length. Therefore, now let's find the total part length. It's just an element of the length that we have found. What is now the total part length? Therefore, the total part length, I hope we can see this. The total part length. Let's use L to represent that. L is equal to the integral running from a to b of our ds, which is what? 1 plus y prime squared, raised by half dx. Yes. Okay. In that case, we have gotten, we can call this one equation asterisk. So in that case, we have got the functional. So what is the functional? Don't forget, we want to extremize our functional, and we use function to extremize our functional. Okay. Therefore, hence, the functional becomes, that is, f over y prime comma x is now what? The whole of this is now what? 1 plus y prime squared raised by half. So that's our what? That's our functional. Okay. Now, for L to be stationary, for our L to be stationary, we use the integral. That does not depend. We use the integral that does not contain y. We use the integral that does not contain y. Now, what do we mean by this statement? Okay. Now, let's look at it. Because this integral does not contain y. This is y prime. So what are we saying here? What do I mean? Good. Now, we recall from Euler-Lagrange equation, that is, del half the y, the partial derivative of f with respect to y, minus d dx of del half the y prime is equal to what? 0. Okay. Now, if our y, like we have said now, if this function L is independent of y, that means this will be 0. This implies that d the x of del f del y prime, okay, is equals to 0. Yes, because why? Because del f del y will be 0 when, since the function now does not depend on what? On y. So with this, now integrating both sides, that is integrating that function, if we integrate that function now, integrate this function, let me call this asterisk, integrating asterisk, integrating, I hope you can see that, okay, asterisk, double asterisk gives what? Gives, partial derivative of f with respect to y prime is a constant. That is a constant. Partial derivative of f with respect to that is a constant. Okay? Now, if that happens, and we know that since, let's continue now. So we can now say that. So let k be our constant. We just assume that k is a constant. Then k can be, it's an arbitrary constant. You can use anything to represent that. Then partial derivative of f with respect to y prime is equals to k. And so what are we saying here? We are simply saying that we have, therefore, del the x over del f del y prime is equals to k, implies del the x, d dx rather, of d, and what is our f? Our f is what? 1 plus, that is our function now, y prime squared raised by half the y prime, okay, is equals to what? Is equals to k. So that implies we have to what? Differentiate this function partially with respect to the y prime. So we have k now equals to, please, I hope you are following, okay? Now we move from there. K now equals to, we want to differentiate partially with respect to the y prime. So this k, this is what we are differentiating now. Okay, with respect to what? Now, half times, we have half. Remember, we are differentiating with respect to y prime. Half. Now, this is like for function of function. So you differentiate y prime here. You have 2y prime. Then 1 plus y prime squared. Raised by minus half. Okay. Yes. That will give us what? K is equal to, this we cancel this. You have y prime multiplied by 1 plus y prime squared raised by minus half. Yes. So now, how does that go now? Which implies k is now equal to y prime all over 1 plus y prime squared raised by half. Is that understood? I hope that is clear. Very good. I hope that is clear. Okay. Now, what can we do here? What you just need to do now is to square both sides. Okay. Now, squaring both sides gives, k squared is equals to y prime squared all over, when you square the denominator here, you have 1 plus y prime squared, multiply it by 2. So the half, when you have multiply half by 2, it cancels out. Fine. Yes. Okay. Which implies, by the time you cross multiply, you have k squared into 1 plus y prime squared equals to y prime squared. Yes. So which implies what? Which shows that When you expand, you have k squared plus k squared y prime squared is equals to y prime squared. Yes. So, which now means what? Collect like terms. We have k squared is equal to y prime squared minus k squared y prime squared. Beautiful. So, which implies k squared is equal to y prime squared into 1 minus k squared. Yes. Yes. So we can arrive it at this. You can see now that dividing both sides by 1 minus k squared, we have k squared all over 1 minus k squared is equals to y prime squared. Fine. Now, to remove the square from each, we find the square root of both sides. Okay, let me write this one here. Now, finding the square root of both sides, finding the square root of both sides gives this will be what? K all over the square root of, that is the square root of 1 minus k squared okay, is equal to the square root of this. That's y prime. Yes, we find the square root of both sides. So which implies, and this is that what k all over 1 minus k squared square root is equals to dy dx. All right? Yes. So when you cross multiply now, very straightforward. When you cross multiply now, you can say that this dy dx now is equals to k all over square root of 1 minus k squared. That implies dy dx, dy is equals to what? K all over 1 minus k squared square root dx. Good. Now, to get y, what do? We integrate so as to remove the difference, the differential constant there. So by integrating, we have y now is just okay. Let's show that the integral of the y is equal to the integral of k all over 1 minus k squared raised by half the x. Okay, or I can better see, I might put my square root there. No problem. I put my square root there. 1 minus k squared. No problem about that. Okay. So now, so what happens there? Because I want to integrate what y is equal to. Now I can bring my k out and have this way. I can bring my k out, but because k all over this is a constant, so I have k all over the square root of 1 minus k squared integral over dx. Yes, I hope you understand what I did there, because the whole of this is a constant. Okay, it's an arbitrary constant, so bring out the constant and now integrate dx. So which implies y is equal to k all over the square root of 1 minus k squared x plus c. So if you look at this critically, you see that this represents, it looks like equation of a straight line. Okay, that means if m is equal to k all over the square root of 1 minus k squared, then we have what? Y is equal to mx plus c, which is our desired answer. So that means the equation joining the shortest distance between 2 points is a straight line, because this is a general equation of a straight line. So with this, we have come to the end of this the problem. So if you enjoy this video, I want you to what? Give it a thumb up, share, and what? And like it. If you are joining us for the first time, don't hesitate to subscribe to this video channel and hit the notification bell so that each time I upload a video, you'll be duly notified. Thank you. God bless you. Bye.